postdoctoral fellow hosted at Technische Universität München and supported by the Swiss National Science Foundation. His research centers around the foundations of quantum advantage. Let us all welcome our speaker.
Hi. Yeah. Thank you very much for the invitation for this presentation. I first want to thank my co-author, Libor and Robert, for this work. And feel free to interrupt me in the presentation. Yeah. Can you hear me properly?
Can you hear me right now?
Yes.
Because I'm not hearing you.
I can hear you. I can hear both of you.
Yeah,
Lindro, okay.
We're fine.
Can you hear me, Lindro? Can you hear me? I think Lindro, you are muted. Something is wrong. Yes, I could. Yeah, same. I think probably the issue is from Lindro's side. Yes.
Yes, because I think I can hear you. Yeah. Fine.
Okay. Okay. Maybe if you don't mind, maybe let's wait for a minute for the intro to. How about now, Lindro? How about now? Can you hear us? I can hear you.
Yeah.
Okay.
Okay.
I can hear you.
Oh, I can hear you as well.
Yeah, me too.
Oh, great. Then let's go.
Yes, so thank you very much for the invitation. And the outline of my talk is gonna be, I'm gonna first start with talking about quantum advantage, circuit complexity, and gate teleportation. So I want to introduce these concepts and what we do when we study those objects. And then I want to present the main result, which is the quantum advantage of gate teleportation in constant depth circuits. And what's really nice about this result is that it gives a separation between two complexity classes, that is unconditional. And And it's a separation that had already been proven, but what we do is we give an alternative proof that is based on a very simple circuit, and it seems that it touches the essence of what is fundamental with quantum information processing. So as I said, the result was the separation was already known, but the proof methods are the proof is new, and it relies on many different methods in quantum information theory. Namely, it used some Lycon arguments, as well as quantum contextuality and some cryptographic techniques. So I'm going to try to introduce a bit, give the idea of why we use these, and focus mainly on the quantum contextuality part to explain how we use this to make the proof. So first, quantum advantage. So for a long time, quantum advantage was mainly the study of efficient computation. And the idea was to separate the class of efficient classical computation, which is P or BPP, so polynomial time or bounded error polynomial time, versus efficient quantum computation, which is a BQP. And one major milestone in this field was the integer factorization, which allows, for example, to break the cryptographic scheme of RSA because of Shor's algorithm. So a quantum computer can do some computation that we think is hard for a classical computer, but for which we're not sure that this hardness is true or not. So it's a conjecture. And two kind of issues with this with these studies, with big complexity classes like P or BQP, is that in the near terms, we're not going to have a quantum computer that's going to be universal and strong enough to solve problems that are in the classes BQP. One of the main errors is because of decoherence and error, and because current devices, they are not, and devices in the foreseeable future, they are not capable of doing error correction, quantum error correction. So the longer the computation runs, well, the more errors accumulate and corrupts the result. And the second drawbacks of these studies is that since these complexity classes are quite rich and large, it's very hard to prove unconditional results. So most results are based on computational assumptions or conjectures, where we reduce the difficulty of one problem to another, but we cannot prove it with certainty, like for the case of integer factorization. And for these reasons, we study constant depth circuits. So the complexity classes of constant depth circuits are, for example, NC0, which is the classical version, where the circuit can be polynomial in size, meaning that the number of inputs or gates is polynomial, and then it's going to be constant in its depth. So the depth is the longest path from one input to one output. For example, here the depth is 3 for the circuit. No, it's actually 4, sorry. No, 3. And the circuit is composed of OR gates, of AND gates or NOT gates, and fan-out gates. And the idea is that these gates have bounded fan-in, meaning that there's a limited number of input for each of these gates. Namely, in the circuits, the OR and the AND takes 2 inputs. And the equivalent, the quantum equivalent of this is the QNC0, which is also polynomial in size, constant in depth, but instead of having classical states and classical gates, we have quantum states and quantum gates with measurement at the ends. So for example, here we have also circuits of depth 3 with some Hadamard gates and CNOTs. And the problem we try to solve is to make a separation between, to prove that there are some problems that can be solved in QNC0 that cannot be solved by NC0 circuit. And important for our proof method, we will also need another class of classical circuit, which is AC0 circuit, which are the same as NC0, so they are constant depth, but the AND gates that are in the circuit can have a non-bounded amount of input. So we're going to make a separation between NC0 and QNC0, but we will also need to talk about AC0 on the way. And one important property of AC0 circuit is that parity is not in this class of circuit, so it's also not in NC0. And this result has been proven in many flavors since then, but essentially what it says is that the naive algorithm for computing parity, which is by doing this kind of Swiss tournament computation, is logarithmic in depth, and we cannot do it in constant depth. And this shows an interesting way why we're studying constant depth circuit, is that the more restricted the model is, the more richer it is in complexity proof. For example, in this case, we can prove unconditional lower bounds on parity for constant depth circuits, which is much harder for larger complexity classes like P or beyond. As I said, there's been previous work separating NC0 from QNC0. The first of these kinds were relying on some hardness assumption, and then came some unconditional separation, but they were based on upon non-Bell inequality violations. And in our work, well, what we do is the opposite. Instead of starting from Bell inequality violation and proving this result, we introduce some new methods to prove the separation, and on the way it proves some new type of Bell inequalities that are more computationally motivated. So to explain clearly what our circuit does, what our problem is, I'll need to explain in detail what teleportation is. So in teleportation, we will have that Alice on top has 1 qubit psi that she wants to teleport to Bob. And now in this tensor network representation, we have 3 wires. And the top one is the qubit that Alice wants to teleport. And the bottom one is a maximally entangled pair between also Alice, but another register, and Bob. And we can see the channel, the teleportation channel, as one that introduces some random polynoise on the way to the teleportation, such that if Bob looks at his qubit before the end of the protocol, all he sees is a completely mixed state, because it's a state that is corrupted by some unknown polynoise, which is some kind of quantum one-time path. And in the teleportation protocol, what happened is that Alice, with her 2 qubits, she's going to make some Bell measurement. It's going to reveal the 2 bits of this quantum one-time path, which is a Pauli matrix. And then she's going to communicate it to Bob. So the state on Bob's side for now is this state. And Alice is going to call Bob with classical communication and give to him the Pauli matrix. And then Bob can remove the noise from his qubit and recover the state that Alice sent. And it's also possible to and now we can exploit this to do gate teleportation. And gate teleportation is that Bob is going to start by applying some unitary on his side, and then Alice is going to teleport her state through Bob's unitary gate. And the result of this operation will... Yes.
So here the state psi A Alice want to teleport to Bob is known, but just it goes through a noise channel, so it's become unknown, or is that true?
Well, the state teleported by Alice is arbitrary, so it can even be unknown by every party.
Okay.
But one way of seeing it is just that Alice brings the state to Bob, and on the way the state gets corrupted by noise, but this noise can be corrected afterwards by information that Alice gains during her measurement, which is this Pauli matrix. So teleportation can really be seen as a noisy channel, which noise can be undone with the right knowledge, if Alice has done the right measurement. And yes, and now this works even if Bob starts with his unitary. So the diagram can be, we can follow the wire. So it starts with the state at Alice, it gets corrupted by noise, and then it passes through the unitary gate, which is what is here. And the problem with that is that in general, if we want to undo this noise, we cannot just reapply the same Pauli matrix on the unitary because they do not commute. So if we do PUP, it's in general not going to be equal to EU. So when we do this, in the end, what we do is a random unitary, but it's not necessarily the unitary that we wanted to apply for the circuit. So in general, we will have that gate teleportation does not allow to apply any unitary with certainty. Now I'll talk a bit about Clifford group and then talk about gate teleportation using Clifford gates. So polygates are gates of this set, which are an I, X, Y, Z. And Clifford gates are gates that stabilize the polygates. And so it's for 1 qubit, for example, it's a set of unitary that will stabilize the set of I, X, Y, Z. For example, a polygate is Clifford. Hadamard is also Clifford. Phase gate is a Clifford gate, etc. And the details of this are not super important for the talk, but one really important property is this one, which is that if we apply a polygate and then a Clifford gate, it's equivalent to applying a Clifford gate and then a different polygate that depends on the Clifford. And this is because of this property of Clifford gates. And this will be crucial to our construction. So I come back to this gate teleportation, but now instead of taking an arbitrary unitary, I only apply a Clifford gate. Now I still have that it's not true that if we sandwich one Clifford between twice the same Pauli, it's gonna be the same as applying directly the Clifford gate. But what is true is this property, that we can commute out the Pauli out of the Clifford, meaning that instead of seeing our final state as a Clifford and then a Pauli, we see it as a different Pauli and then a Clifford. And what we can do, and so this Pauli can be computed by knowledge of the initial Pauli gate and from the Clifford gate. And what it allows us to do is that this correction can be done after the teleportation. And it can even be done as post-processing, meaning that we have a circuit where we measure right away the state at Bob's side, and then depending on the Pauli, we flip the result or not. And it will become more clear why we're doing this in the next slide. But now, for now, like the important part is that this noise can be seen as here. So why is it important? Let's say that we want to compute a circuit of multiple Clifford apply on a state, one after the other. So we want to compute C3, C2, C1 applied on psi. Then we start with psi, which is arbitrary and can even be unknown. Then we apply the first noise, and then the first Clifford, then the second noise, second Clifford, third noise, third Clifford. We follow the wire. And then we end up with this state at the bottom, which looks almost like what we want, but there's a lot of Pauli gates that are interjected in between. And then we use this property of commutation to see that our first Pauli gates, we can see it as a different Pauli gate that is applied after the first Clifford. And then we can do the same thing with these two and commute them at the end of the third one. And finally, we can group them and put them all at the end of the computation. And now what we see is that the result of this computation is going to be the state that we want plus the three Clifford gates with at the end some Pauli noise, which is one random Pauli matrix. And now, given the knowledge of P1, P2, P3, and C1, C2, C3, we can recover what this noise was. And then, after the measurement, we can correct it if we want. And we will see that for our construction, we don't even need to correct it. So we will just, it's just important that the noise comes after all of the gates operation that we've applied. Now this seems like a very complicated way to just do a computation C1, C2, C3 on a qubit. But what's the power of this is that we can, instead of doing it in serie, we can do it all in parallel, because this circuit is essentially a parallel circuit. So if we don't wait and we do all of the computation at the same time, then we can compute this state. So essentially what we've done is we've parallelized the computation C1, C2, C3 at the cost of one random Pauli error at the end on the left side. And this Pauli depends on all Ci and also on all intermediate measurement, where on the right side of these, so on the right angle of these circuits are the Bell measurements. So we see that we cannot take any computation that is Clifford's and in serie and transform it in a computation that is done in parallel, but we can do something that is close to it, that is almost it. And we will use this to prove the quantum advantage. So if I rewrite the circuit, it looks like this. So we have the inputs on the left side, which are some Clifford gate. We have the outputs on the right side, which are Pauli matrices. These can be seen as the outcome of the Bell measurement that are done. And these are maximally entangled state on the left, and on the right, these are Bell measurement that are done. And I'm going to stop writing this notation with the noise, and I'm just going to replace them by Pauli gates. And I'm going to assume that the circuit is done on a circle, which I'm going to represent by this cylinder. So the qubit at the bottom is linked to the qubit at the top. And it's symmetrical in its character. So this is the single qubit gate teleportation circuit. And our task is to simulate this quantum circuit, which by definition is in QNC0. And we will prove that the simulation of this quantum circuit cannot be achieved by a classical circuit. So our task is sampling from the probability distribution defined by this quantum circuit, conditional probability distribution. And our notion of sampling is going to be very strong or very weak, depending on how you see it. So it's a possibilistic simulation. And the idea of possibilistic simulation is that we're just going to look at the support of the probability distribution, and we're going to accept the simulation as long as it outputs something that has a non-zero probability of happening. So even if it has a very low probability of happening, when you make a measurement, as long as the probability is not zero, we're going to accept it. So it's a relation problem, input-output. And this form of simulation is the weakest form possible. So it gives the strongest result in terms of separation. And it can be considered as adversarial sampling. And to make it a bit more concrete, well, here's a simple example. If for our circuit we want to make a Z measurement on the zero state, then the possibilistic simulation must output zero because the outcome 1 has probability 0. So only the outcome 0 is possible. But if we're making a Z measurement on the plus state, then since both outcomes are possible, usually they will have probability 1/2. But here we don't care about the probabilities. We just see that they are both non-zero, so both outcomes are possible. So we will accept the simulation if either of these output is obtained. And we will call such outcome a non-sharp because it can take two values, while the other one is sharp because there's only one value that is possible. And this will be useful for the tomography step at the end of this presentation. So our whole construction is a reduction to the hardness of parity. So what we show is that if there was a classical circuit to simulate possibilistically the quantum circuit defined on this cylinder, if such simulator existed, then it could be used by an AC0 circuit as a subroutine to solve parity. And we've seen that, I've explained in the beginning that parity is not in AC0. It cannot be computed in constant depth by any flavor of constant depth circuit, classical constant depth circuit. However, the result does not imply anything about parity being in QNC0. So to be clear, our circuit does not compute parity. It computes some other function, which if it was simulable by a classical simulator, then it could be used to compute parity. And in fact, parity is not in QNC0. So what we're showing is that the problem that the probability distribution that the quantum circuits simulate could not have been done by a classical circuit, because if a classical circuit could have done it, it will also be able to compute parity. And parity cannot be computed in constant time. And this leads to the question of can we extend these results to compute more, to have some quantum advantage in some case where we can exploit the quantum advantage for more useful and primitive. Yes.
You said that the parity is not in QNC 0. So do you have a reference for that, or you're just saying that because it's built upon the NC0 structure?
I will need to look up a reference. I don't remember.
Okay. And another perhaps naive question, but why did you put the circuit in this cylinder shape?
So it's to
important.
The fact that the bottom of the circuit is linked to the top of the circuit.
But this is going to help further on, or?
Yes, we're going to use this. So the circuit is like n EPR pair, and they're all linked to the next one, and it has a cyclic structure, meaning that the last EPR pair is linked to is going to be measured with the first EPR pair using a Bell measurement.
Okay, thank you.
So our circuit has a 1D structure, but it's in a circle. And now, I want to talk mainly about this magic square tomography and about how we actually encode and decode this parity and solve this parity problem into our circuit. So the idea is that we're going to split our circuit into two parts. One part is going to encode the problem of parity, and the second part is going to run the tomography. So the idea of tomography is you make multiple measurements to be able to identify what's here. It's a state tomography, so to identify what state it is. And in our case, we're going to use the classical simulation to simulate many measurements made on the quantum circuit. And a priori, it's not obvious how to separate these two parts, meaning that if we modify the inputs of the tomography, it could change completely the outcomes of the problem on top, meaning that the first step, it gives a quantum state, and we want to simulate many measurements on this quantum state. But if every time we change the measurement, we also change the state, then we cannot do tomography. And the first reason, and the first ingredient of the proof is to be able to have a construction where we can change the tomography, but have some promise that it's not going to change the state over which we're doing the tomography, or that it's not changing it too much. And I won't go into the details of exactly how it works, but essentially there are two parts to the argument. One is that we use these light cones of constant depth circuit, where the idea is that if the circuit is constant depth, for any input, if we change it, it's going to affect at most a constant number of output. For example, if the circuit is length D, and that we only have n gates with two inputs, then the number of outputs is going to be maximum 2 to the D. So it's constant, which means that there are some inputs that when we change them, it doesn't change. There are many outputs that are not affected by changing one input, and changing one input affect at most a constant number of output. So it cannot change all of the circuit because it's constant depth. It's going to change just a small part of the circuit. And the other ingredient that is important is the cyclicity of the circuit, so that we can rotate that we can commute a constant number of polygates, and I won't go into the details. So encoding parity. So this is the maybe most central part of the argument, is that for the one subpart of our circuit, the inputs are going to be either Hadamard gate or the identity gate. And the idea is that the product of those gates is going to be either equal to identity or equal to Hadamard. So if we can see, we sample x1 to xn at random, and then the sum modulo 2 of these variables going to determine if the sum of these gates are identity or Hadamard. So solving the parity problem here means finding out if the total number of Hadamard gate is even or odd. And we can see it like this. So we start with phi plus on top, with Alice and Bob. And then the Bob part, we run it through all of the circuit, and it picks up some Hadamard gate and some Pauli gates. And at the end, what we obtain is a state that looks like this. Because of this property that the noise commutes, we're going to have that if the number of Hadamard gates was even, we will have a state that looks like the first one. And if the number of Hadamard gates was odd, then it's going to look like the second one. And here it's important to note that to be able to compute this Pauli noise, this problem is as hard as solving the original parity problem of computing how many Hadamard gates there was. So we're not going to be able to directly remove this noise, but what we're going to do is we're going to be able to leak some information even in presence of this noise during this classical simulation. So the next step is essentially how can we distinguish these two sets of state even if they are completely mixed. If you have only one copy, this state is completely mixed. So the idea is how can we trick the adversarial possibilistic simulation into leaking information about what is behind this Pauli noise, behind this quantum one-time path. And I will talk more about it in the next slides, but the idea is that we're going to do this magic square state tomography, which relies on quantum contextuality. And it's a way to make measurements. We're going to make 6 measurements of, and it's going to reveal some information about the state. And then we're going to do Killian randomization, which comes from cryptography. And the idea is that we can do a local transformation on all inputs, and this will give some global obfuscation that can allows us to repeat the precedent step of magic square state tomography, but obtain new information. So the first step gives some information, and the second step allows us to kind of amplify and gain more information until we get the information that we need to be able to discriminate the two states. However, the steps requires a de-randomization with the AC0 circuit, and this is where this AC0 circuit comes into play. I won't explain in detail how this transformation works, but basically it's given by this equation, where we are changing locally each each input, we do some transformation, but it allows us to, in AC0, to still be able to track the change. But for the NC0 circuit, it's going to be impossible to tell. Okay, but so the main idea relies on magic square tomography, which yeah, it's a really nice idea, so it's why I wanted to present it. I will start with an example with 1 qubit, and it will not work. And this is why we use 2 qubits, and we need this cyclic structure to be able to have 2 qubits. So let's pretend I wanted to distinguish a 0 state with some polynoise from a Hadamard state, so a plus state with the same, yeah, with some polynoise. I want to be able to distinguish both of these set of states. So in other words, given some random state, I want to find whether the base is 0, 1 or plus and minus. And in this adversarial possibilistic simulation context. So if I'm given a single copy of the state, in quantum mechanics, they are undistinguishable. They are both represented by a completely mixed density matrix. So I make one measurement, I obtain one completely random outcome, and that's it. I will not be able to tell them apart. But if I do a classical simulation, then I can rewind. I can make a measurement, then rewind and say, okay, let's say I made a different measurement, and then I make a different measurement. So effectively, like this classicality allows of the simulation allows us to make a measurement on many copies of this unknown state. And if I can make many measurements on many copies, well, usually I will be able to access the whole probability distribution of the measurement. And normally it's enough to be able to tell whether I have a 0, 1 or plus or minus. However, in this context of possibilistic tomography, it's not going to be enough because we don't sample the probability distribution. What we sample is only the support. And for example, if for my first measurement, I measure in the 0, 1 basis, and it tells me, yes, the state is a 0, then I know that, okay, the state couldn't have been 1 because this had probability 0, but it could have been either 0, plus or minus. And if I make a second measurement, I measure in the Hadamard basis, I obtain, yes, the state was a plus. Then it's the same thing. I know for sure it's not a minus, but I cannot tell if it's a 0, a plus, or a 1. So in both of these cases, we will have one state which belongs to the first base and another state which belongs to the second basis. So we cannot distinguish them. And this is where the magic square comes in. And the idea is that instead of trying to distinguish 1 qubit, we're going to distinguish 2 qubits. So what we want is to simulate measurement on these 2 states and tell them apart. So essentially we have these two set of state, and we're not going to be able to tell which one of these states it is in one set, but we're going to be able to tell which set is being measured. And again, this is not possible using a single measurement and quantum mechanics, but it's possible because we can simulate many measurements using this classical simulation. And the idea of the magic square, if you're unfamiliar with it, is that it's a set of measurements that we represent as a square, and each element in a row or a column are commute with each other, so they're compatible, but elements in different rows and different columns are not compatible. And note that the Pauli matrix Y can represent by IXZ. then the property of this magic square is that if we multiply any element of, if we take the product of every element of one row, for any row, well, it's gonna, the product is gonna be a plus identity. And if we take a column, then it's gonna be minus identity. So in computer science notation, what it means is that the parity of the outputs of a row is going to be 0, and the parity of the outputs of a column is going to be 1. And now we see that we cannot assign one fixed value to each observable, because we cannot have a square where this property of the parity of the line and the even parity of lines and odd parity of columns is respected. For example, here we have that the property is respected for 8 squares, but for the last one, well, we need to have 2 values. And how does this relate to our problem of tomography? Well, is that when we're going to do the state tomography, the procedure is we're going to make this classical rewind to make all 6 measurements. So we're going to measure the 3 rows and the 3 columns. And normally in quantum mechanics, we can only make one of these 6 measurements. But here we're doing a classical simulation, so we can do these 6 measurements. So we're going to measure every observable 2 times, one in a row and once in a column. And at least one observable is going to be assigned 2 different values. Like here, it's the observable in the lower right corner that is assigned the value 1 and 0. What it means is that when you measure the line, the row, you measure 1, and when you measure the column, you measure 0. So you see that, okay, well, this square could take 2 values. And how does it help us for our problem is that we have that the set of states 1 here on top is sharp for these 3 observables. What sharp means is that it can only take 1 value, while the second set of state is sharp for this set of observables, which means it can only take 1 value. So if we obtain that, and we do our magic square measurements, and we obtain 2 different values for, so a value for the column here and for the row here and the column here that are different, for example, in this square, well, we know that the state must have been from the second family, because it cannot have been from the first family, because only 1 value could have been taken here. So it's essentially what the magic square promises us when we do this measurement is that we will know that at least one observable is not sharp. And then if we have, for example, here it's not sharp, then we know that it must have been the other state that we measured. And if we have it here, we know that it's the first one. And it can never be, for example, here, because this one is sharp for both. However, there's some case where neither of the observables are sharp for neither families and neither sets. So in which case we don't gain information. We know that, okay, this observable is not sharp, but it doesn't allow us to distinguish between 1 and 2. So we see here that there are 2 values that will allow us to distinguish, and the other values that will not allow us. And this is why we use this Killian randomization. So we're going to repeat this whole procedure. And by repeating it with this randomization, every time we obtain 1 random observable that is not sharp, and once we've had enough of them, we can tell for sure that which set of states are we measuring. So it allows us to distinguish between this state and this state without knowing what this Pauli matrix is. So essentially it allows us to find the base, and this basis depends on whether we've applied even or odd numbers of Hadamard gates. And so it allows us to solve the parity problem, because we can distinguish between the product of all Adamars is identity, or for even, or one Adamar for odd. So the conclusion is that our problem was, can NC0 circuit simulate QNC0 circuit? And our main result is that this very fundamental circuit of single-qubit gate teleportation cannot be in NC0, doesn't belong to NC0. Or more precisely, the task of the relation problem of possibilistically simulating the conditional probability distribution given the Clifford inputs does, if it was in NC0, then parity will be in AC0, which is too easy, which is a contradiction, so it doesn't belong to NC0. And here this poly means that the circuit can be non-uniform. So it's so it applies both to uniform and non-uniform circuit. So what new prospect does this open? So the first one I've already mentioned is that can we use this to build some exploitable quantum advantage for less artificial computing tasks? And can we have stronger separation? For this, it will mainly need to go beyond like cone arguments. And then maybe we can hope to have AC0 or NC1, so the unconditional separation, using similar arguments. And it will also be interesting to find and analyze more these computationally motivated Bell inequalities, because they are very different in nature from the usually studied one in physics. So thanks a lot for your attention. And here's the references. And I'll be happy to answer any question.
Thank you very much for the seminar. Now we're going to open up for questions. So if the audience has any questions for our speaker. Okay. I have one, at least.
Yeah.
If you go back one slide.
This one?
Yeah, to this one. Okay, I think I got the main idea of how you make this work, but it's not really clear to me how this rewind is done. Because I think on the previous slide you said that this was a classical feature, right?
Yeah.
And I assume that you're using QNC0 circuits to do that? So how is this done exactly? Like
So
there's a circuit or some construction that you could show, or I don't think it was clear to me.
Yeah. So what happens is that we encode this problem of parity into one sub-circuit, and then the other part of the circuit we're going to change the inputs, and what it's going to be is that for each combination of inputs, it's going to simulate a different measurement on the state that was produced by the top circuit. So we can see that like the outcome of the circuit of the sub-circuit that encode parity as outputting some quantum state, and then using the rest of the circuit, we're going to make different measurement on the quantum state. So we're going to, for example, use some inputs, notes what the answer is, and then change the inputs, and then obtain a second answer, and then change the inputs many times like this. And then the first inputs will correspond, for example, to measuring the first line of the square, and then the second rounds of inputs, the second line of the square, etc. And this is and this is how it will work. But it's actually quite complicated how this encoding of the tomography is actually implemented. But the idea is really that using different inputs to the circuit, we can have the promise that we're doing that we're simulating different measurement on the quantum circuit.
Okay. At the beginning, you said that you do not really show that the QNC0 can solve parity, right? So, yeah. I mean, I'm not sure how to. Because it's not as if you have some advice as well.
Some advice. For our circuit, we use non-uniform circuit. So we can allow some advice.
And the AC0 circuit is only used on the Killian randomization? Was that
exactly? It's to be able to de-randomize here. So we're gonna, like when we make the measurement, we have some every time we obtain some random observable that is not sharp, and to be able to obtain all of them in a deterministic manner, we need to do this de-randomization, which is given in this paper.
Okay. And you can do this with a probability that even if it's small, it's enough for you guys, right?
Yeah.
Or do you have some? Okay. Okay, that's interesting. Okay. Well, for now it's good for me. Thank you.
Yeah. Thanks.